So today I'd like to talk to you about how I revamped my introductory mechanics course to combine computational modeling with video analysis. I call this structure Capture, Code, Compare. We'll talk about what each of those steps mean in just a minute. First, we're going to talk about what motivated me to make this change to my intro class about wanting to see students engage in a little bit more sense-making with their computational models. We'll talk about the Capture, Code, Compare structure. Then I want to spend the bulk of our time together looking at some example activities from this course. And then I'll wrap up by talking about what went well and what I would like to improve in the future. This change to my class was motivated by me noticing my students didn't think that their computer models actually described anything in the real world. They would say things like, "This is interesting, but it's just a model. This code doesn't take everything into account." Now, if I asked the students a follow-up question, like why do they think this, they really didn't have a good reason. They just had this lingering sense that their computational models were never good enough. So this could be attributed to a number of reasons. Do they think that an intro class can't be very accurate? Is this a manifestation of general distrust in science? Or have they simply never been taught how to compare models with measurements to see how well a model matches the real world? So I made it a learning objective for my course that students need to be taught how to compare their models with the real world. So I revamped my Intro Mechanics course to follow this Capture, Code, Compare three-stage process. You can find the course page on Trinket at this link here. So at the beginning of each activity, the students had to capture an experiment, an activity, some sort of event involving motion in a video, and then study that motion with video analysis using Tracker. In the second stage, students had to develop or modify a code that would reproduce the motion in a computer animation. So for this, we're using VPython in the Trinket environment. And then finally, the students at the end of each activity had to compare the results between the video that they captured and the simulation that they developed. So this comparison could be as simple as looking at the motion in the video and in the animation and saying that they move in the same direction or that they have the same type of shape of trajectory. We get into a little bit more detail when we graph the motion, so that the graphs need to show that they're the same type of shape, so they got to both be linear or both be parabolic or something like that. And they can also compare important values. So if we've got a linear graph from the video and a linear graph from VPython, they can compare the slope of the two to see how well they match. So there's a little bit of scaffolding there in terms of what the students are comparing and how in depth they're going. And the goal for this stage is to celebrate the victories, so what worked well, and explain any discrepancies that arose between the two sets of results. I assessed this by assigning the students a letter home each week, so they had to write to somebody not in the class about their activity. And I'd like to show you a few examples, starting with the example from the activity from the first week, which is when students had to walk at a constant velocity in front of the camera. Pretty straightforward. I wanted to have a simple activity for the first week so the students could become accustomed to both the software and the analysis process. Here are the results this student got from Tracker. They've got a position versus time that is roughly linear. They're speeding up a little bit here at the beginning, but they also noted that because this thing goes down and to the right, that gave them a negative velocity because they are walking to the left. So it's a great opportunity to already talk about directional signs. Here they've got their graph of their velocity versus time. You can see once they get up to speed, it's relatively consistent. Here they have to recreate this motion in VPython. You'll notice that this student forgot to assign a negative sign to the velocity, so this ball is moving to the right while the student is moving to the left, but they end up with roughly the same amount of time. That's about all you can really compare on a constant velocity walk, is put in the distance that they need to travel and then see how much time it takes for the ball to move across the screen. And then at the end, they have to compare the two. This student is probably going into a little too much detail on such a simple activity, but it's important to see that they are referencing back and forth between the video and the code and putting those really side by side and thinking of them as two things that should match each other. A few weeks later, we get to spring oscillations. Here we've got the tracker results for the position of a mass on a spring and its acceleration. Students can pretty easily get the period off of this graph. And then we model that in VPython over here. Again, pretty straightforward to get the period off of the graph. They can also then explore, changes to the period based on the mass or the spring stiffness. But because the students are engaging in the same set of analysis techniques each week, we're able to go into pretty good depth with analyzing the results. So here we've got a graph of the kinetic potential and total energy versus time for our VPython simulation. They get a pretty flat total energy curve. They need to decrease their time step a little bit. They get a similar graph from Tracker, and they're able to see that the energy is roughly conserved there as well. It's also incredibly easy in these environments to create a phase space plot. So here, these students are graphing their velocity versus the position. They're getting an ellipse, which is another picture of conservation of energy. Over here in VPython, they also get an ellipse here. We get to projectile motion a bit later in the semester than usual because I want the students to be able to talk about things like the effect of drag on their projectile. So here in Tracker, the student is examining I believe this is the horizontal position versus time. And as you can see, they're envisioning this thing as deviating from a straight line. So they're calling this the line without drag and this the line with drag. And they're attributing the difference between those two to the drag force, to being energy lost due to the drag force. So they're already, without even being prompted to, they're thinking in terms of energy. They're thinking in terms of what is robbing this thing of its kinetic energy as it moves forward. Over here, similarly, they've got the horizontal and vertical positions versus time. And again, their goal is to get this horizontal position graph to match this blue graph over here. And the only way they can do that is by adding drag. So they get a projectile motion code that has no drag. They have to add the drag and then adjust the drag coefficient in order to get those two to match. And they've got their comparison down here. You can tell that they're comparing both the graphs and the values, so they're actually able to come up with a conclusion that their model works pretty well. So this has been a very successful revamp of my intro mechanics course. Most of the students eventually learned to make the comparisons in a pretty satisfactory manner. Also, most of the students were able to learn concepts successfully through the activity. These activities are also much more open-ended and a lot more enjoyable for the students, and it's nice that the skills that they learn can transfer between activities. I also found when we had to teach online in March 2020, like everybody else did, that this process was easily adaptable to an online learning environment because the only piece of equipment the students need is a cell phone with a camera and a tripod. And it's different enough from high school physics that regardless of whether students had a high school physics class or not, they were all kind of on the same playing field in terms of challenge level. Some students were a little bit too focused on surface features, particularly the speed of the animation versus the speed of the video, which we know is irrelevant. And their learning was not always demonstrated in their write-ups, and I'm exploring whether that's a conceptual issue or a writing shortcoming. And then, of course, I would like to think of how to extend this process into Intro E&M. Thank you so much for your time.